Hi, my name's Daniel Hayden. I'm a postdoc here at MSU, and I'm going to try and explain to you in around 2 minutes how we do searches at the LHC. I'm a part of the ATLAS experiment at CERN, and how we might look for some of the new physics that I'm currently researching. So the first way that we'd like to think about this is when we have the proton-proton collisions, which the LHC provides. Essentially, we're colliding protons upon each other to try and create particles, some which we know about, and hopefully some that we don't currently know exist, but we theorize do. So we might create a new particle. Let's just call it the Z prime. So that's one of the particles I'm looking for. And then upon creating this particle, because it's so massive, usually it will decay very quickly into components, which we then use our detector to analyze and record. And then our job is to kind of take those particles that they decay into, known ones such as electrons, muons, even jets, and try and add them back together to work out what the mass of the particle was that was created by the LHC. So the way you can think of that, the way that we actually do this, is we use histograms. So you may have done this in maths already, but we're applying a physical meaning to these now. So if you have a histogram here, and we're trying to work out the mass of the particle that we might have created, a new particle. So let's say along the x-axis here, that if we record something that's as light as a feather, then we'll put it in this bin. You have to excuse my drawing. If it's as heavy as a house brick, so heavier than a feather, then we put it in this bin. If it's as heavy as a house, let's say, you put it in this bin here. And if it's as heavy as a block of flats, then you put it in here. Okay, so again, you have to excuse my drawings. So of course, we have to do this millions upon millions of times, and every time we record an event, we'll add it up here for the number of events we record of that mass on the y-axis. So let's say we record our first event and it's very light, then we'd add an entry here, and then we might, as we collect more data, we might find that from all the physics we know about, we expect this many events, okay? And then we would expect, then let's just say our expectation is that the heavier the particle gets, the less we detect it. So we would expect this kind of distribution, okay? But now let's say that we actually do the experiment, we actually run the LHC, and we see what we get. So let's say that these points here, I'm going to say a date of what we actually record, and let's say that we see here kind of what we expect, but then let's say that we measured a number of events with this mass much higher than we expected, and then back down here to what we expect. So this is saying that there's something which we haven't currently accounted for in our knowledge of physics. So there's something new. And what that new thing represents depends on its mass and other properties that we can measure at the LHC. So I'm gonna put an overlay here that you'll be seeing on the screen currently, and this is now what you're seeing is the real version of what we do. So now you can see there's much finer binning, and you can see all of the coloured in regions of what we expect, and the dark points are the data that we actually measure with real data from the LHC, and you can see the numbers on the y-axis are now in the hundreds of thousands of events, and this is why it takes so long to collect data and bring out results. And then you can see in the hollow lines overlaid is what some of the new physics that I'm looking for, called a Z prime, might look like. But as you can see, we haven't collected enough data yet to actually see if the Z prime may exist. But we're still hopeful that that might be the case. Now, you may be asking yourselves, what does this Z prime mean? You know, I've been mentioning it, I say what it might look like, but why would you want to look for this? I mean, it's obvious maybe from the standpoint of when we talk about the Higgs boson, you know, you say, this is something that can explain why mass is given to the particles in the standard model. You know, it sounds very big and impressive, and it is. But there are other things that physicists are looking for as well. So when I say the Z prime, this is a particle that's predicted from many theories called grand unified theories that try to tie together some of the other forces of nature which currently seem separate. At some energies we expect these to become one in the same force, and a Z prime is just an example of one of the particles that the theory, grand unified theory, predicts would be created in many cases. Also some supersymmetry scenarios which you may have heard of. And there are many other things that we look for at the LHC as well. So finding the Higgs is just the beginning. It's not the end of the story. It might even point us in the direction of some more other interesting new physics to look for. Another particle that I'm looking for is something called the graviton. So this actually involves extra spatial dimensions. So we currently know, obviously, about our three space-time, so 3 space and 1 time dimensions. So usually we talk about x, y, and z. And then, of course, we have all of that going along in time to give us our 4th dimension. So we have 4 space-time dimensions. But one of the problems in physics at the moment is that no one understands why gravity is so weak. Now, you may think, well, it's not that weak, it's holding me to the floor. But if you think about it, if you pick up a piece of metal with a handheld magnet, what's going on there is that small handheld magnet is winning in a tug of war between this small magnet and the gravitational pull of the entire Earth. Okay? So you can start to appreciate how weak the force of gravity really is compared to the other known forces of nature. The strong force, which holds protons and neutrons together, the weak force, which accounts for decays of particles in many cases, and electromagnetism, which is electricity and magnetism, such as the magnet I was just talking about. So there are many aspects which we're still trying to understand in physics, and the LHC is a prime vehicle to do that. So one of the leading theories for why gravity might be so weak, as I was mentioning, is with the use of extra spatial dimensions. So maybe it is that we live on a 4-dimensional brain. So you could just draw this as a sheet, let's say, so drawing it on 2D, but let's imagine we all live on this world, the Earth is here and everything. And then that through an extra spatial dimension, there is another brain somewhere else where the force of gravity exists. So maybe that all of the normal forces of nature and everything as we experience here, but then there's another brain where the force of gravity is located. Okay, so I'll just put G here. And think of it like a watering can as you water your garden with small holes. Perhaps the force of gravity here is as strong as all of the other forces we measure and feel, but that because of this extra dimension it gets diluted by the time the strength gets to our 3 space and 1 time dimension. Perhaps it's weaker and therefore we feel kind of a watering can effect. So a sign of that would be to measure a particle called the graviton, which would be an extra tensor boson that we would measure and is theorized to exist. And that would decay, we would create at the LHC at these very high energies, and would decay into particles that are predicted, such as electrons and muons, which, as I described before, we could add back together and figure out exist. So this was just to give you a feel that, there's lots of physics, some that you may have not even heard of before, that is being researched at the LHC and is trying to answer some of the deep questions we have in physics at the moment.